Okay, good morning, good afternoon, good evening. Thank you for joining us wherever you are around the world. Welcome to today's Siemens Global webinar. Today's topic will be looking at front-loading electronics cooling simulation with CAD-embedded CFD. Okay, now that we have the corporate bio over with, I'm delighted to have as your speakers today. We have Mr. Chris Watson, who's Technical Manager for FLOEFD, and we have Adil Ali, who's a Solutions Consultant for 3D CFD at Simcenter Americas. Their bios are up on the screen. Chris is, as I said, Technical Manager for FLOEFD products. He is responsible for technical leadership of FLOEFD product line within North America. So very warm welcome to Chris. And Adil will be giving a demo. Adil has been working as a virtual analysis engineer for over 6 years and previously held CAE analyst roles in companies such as FCA and Exa Corporation. He joined Siemens in 2018 and has been serving as a solutions consultant. Without further ado, gentlemen, let me pass over to your first speaker today, Mr. Chris Watson. Hi, Chris. I've just passed you the ball and unmuted you.
All right. Well, thank you very much. Let's go ahead and get started today. As noted already, our topic is front-loading electronics cooling using CAD-embedded CFD. So let's start with the topic of electronics cooling itself. Certainly it is an increasingly important aspect of product development as, we continue to trend towards more electronics and electrification in seemingly everything these days. You have smaller electronics, or basically more electronics being packed into smaller devices, smarter devices, devices that seemingly everywhere, and all of these systems needing to be connected. And basically, it gives rise to various challenges in product development. Certainly the need to increasingly innovate. And while doing so, doing it under increased time to market pressure. The devices that are being designed are increasingly complex from a standpoint of electronics, and reliability is, as with everything, it's always been a concern in product development, and certainly at the minimum from a reputational concern to your enterprise, is if you get some of these high-profile failures, but increasingly they're more consequential. Where let's say your smartphone dies on you, certainly that's inconvenient, and we can't seem to get along very long without our devices. But if you're talking about an autonomous vehicle that relies on electrification and that is a failure, that's certainly a lot more consequential. So reliability is certainly top of mind in product development. And really a lot of the cause of reliability or failure in these devices, a good portion of it is thermal related. If you look at that pie chart there, there's data that shows that really over half of the failures are temperature related, with things like vibration and humidity making up another portion of it, and thus a smaller portion. So certainly, accounting for thermal performance as you're designing a product, electronics product these days, is critical. So as you look at your challenges in product development, of course, always the classic, considerations of needing to lower development costs, and as mentioned already, getting to market faster, all while making more innovative and better performing products along the way. And with those pressures, you give rise to bottlenecks in your process. And certainly accounting for thermal performance as you're going through design, there's various ways of doing it, either experimentally or if you're trying to use tools, virtual tools that will give you that type of feedback. As you try to, lower the time to market, these bottlenecks become, increasingly apparent. So, and of course, all of this, with reduced operational risk and compliance in mind as well. So, regarding the whole, bottleneck in the design process aspect, that gives rise to this first topic of our overall discussion today, this idea of front loading. So what is front loading about? So generally speaking, we'll talk about it with respect to electronics here shortly, but generally speaking, it's the idea of being able to take this type of technology. In our case, CFD, it can be other technologies, but specific to, doing, this thermal analysis, and moving this, if possible, earlier into the design process, being able to do analysis and get feedback as to how your device is performing from a thermal point of view earlier on at a point when it's easier and cheaper to make changes, potentially being done by, let's say, a wider group of engineers that can do a lot of this early work, and while the design is changing, know that you are accounting for thermal issues appropriately. So that's this whole idea of moving sort of this virtual analysis feedback earlier in the process where it's kind of most useful to make use of that data. So the tool that we are going to look at today that from Siemens that addresses it targets this whole notion of front loading and expanding CFD to maybe a broader group of engineers is FLOEFD, Simcenter FLOEFD. So what are the attributes of it that lead to that realization of front loading? So certainly the CAD embeddedness, the way that you can work directly on your native CAD model in a host of the leading CAD systems. We'll talk about this in a bit more detail here shortly, but that's a big part of it, and it's been the focus of FLOEFD for going on 20 years now, is taking CFD and putting it in CAD in that engineer's environment to do analysis. Along with that, that alone is not enough. Being able to work directly on your CAD model without needing to essentially to simplify it at all is a big time-saving aspect. Having the supporting technology that can handle that type of approach, and for us, it's using what we call these smart cells, goes hand in hand with the ability to use these real CAD models, and then having some underlying technology to tie all of that together from the solver side. So all of this leads to design exploration being efficient and easy to use in this environment, in this tool that can be incorporated earlier in the design process. So this is generally what we're talking about with front loading with FLOEFD. And I'm going to pick just a couple of these topics and just flesh them out a little bit further here. So starting with the CAD side. Certainly we're embedded in the major CAD systems out there. Obviously, the Siemens CAD tools, Solid Edge and NX. The animation that you're seeing on the screen right now is an example in Solid Edge from Siemens. The demo that you're going to see shortly is going to be in NX itself. But we're not limited to just the Siemens CAD tools. Certainly if you're using Creo from PTC or CATIA or with standalone using potentially SolidWorks models, we have versions to handle many of the other popular CAD systems. In fact, some of those other CAD systems are some of our longest standing integrations, so it's very mature, robust integrations that we've had for 15, 20 years now. The advantages of this, beyond just being in the CAD interface, is the approach that we take with respect to the fluid space recognition. This is CFD. It's going to be a fluid region, let's say potentially an airspace and an electronics problem that needs to be modeled. The way that that's handled in FLOEFD is very easy and elegant. The ability to work on the native CAD model. This isn't a exporting out of CAD into another package. You're working directly on the native CAD model with the inherent advantages of that, of being able to easily make changes to the model. So you set up your analysis directly on the CAD model itself, applying inputs to the CAD model, the results are being viewed in the CAD environment directly on your native CAD model. And then this all leads to, like I say, easy ability to make changes and see the effect of that. And one big aspect of it is, besides the native CAD model, is that it's actually, the assembly that you really haven't done much with respect to preparation or what's classically required for analysis preparation, defeaturing and simplifying and these things, to get ready to do an analysis in CAE tools generally, just being able to give it that full assembly. And so that leads to the next technology that really is required to support all that is a meshing approach that can deal with these types of complex models that haven't been simplified. So our meshing approach, when you do a technology like CFD, there's this mesh that's built that's required to solve the analysis and give you a solution. This is where a lot of time historically is spent in trying to prepare a model for CFD, and this is one of the main strengths of the software, is an approach that is easy. It doesn't have a lot of requirements with respect to expertise from the user, and it can really just chew up these complex assemblies with very little intervention. Now, if you do become a more experienced user and you want to invoke some meshing control, you can. It is available, certainly. So I don't want to give the impression that it's just this black box approach. It's flexible, but the real power of it is being able to just take a unsimplified CAD model and with very few inputs get a mesh very quickly, which is a big time saver and gets rid of a big bottleneck in doing CFD generally. And the third aspect that sort of supports all this are some of these underlying technologies. The ability to generate that mesh like that it's great, but to support that style of mesh, we need to have some additional smarts, if you will, built into the solver, built into the underlying math that goes into the solution process. So we incorporate some innovative modeling to handle things like how the boundary layer is treated and areas where, let's say, the mesh is coarse relative to what you would classically need in CFD. So this is all being handled by the software in a somewhat transparent way, allowing both the speed to get through this process that you desire, as well as opening up to more people being able to do this type of analysis. So that's FLOEFD and front loading generally. As we start to focus this on today's topic, we can start to look at application areas within electronics that FLOEFD could be applied to. So here is just a sampling of types of applications that you can use FLOEFD for, and IGBTs all the way down. You can see them, see the examples on the screen there. So certainly it's applied to a range of these thermal problems in the electronics cooling space. But rather than talk about all this, I think probably the most compelling way to see it is in a demo itself, and take us through an example. So for that, I'm going to pass this off to my colleague, Adil Ali, and he is going to take us through an example.
So let me explain the problem a little bit before I jump into the demo. So the geometry you see is, we came up with this in-house. It's supposed to represent an autonomous sensor fusion box. These are the kinds of boxes which are being used for, autonomous mobility purposes. So they have high power density electronics, a lot of processors. They support multiple cameras, multiple LiDARs, etc. So the top enclosure that you see has the printed circuit board. The printed circuit board is mounted on these cold plates through which we have coolant running through. The coolant then goes to the lower enclosure, and then it passes through sort of a radiator. And then we have a fan in the lower enclosure that extracts the heat. And then the coolant is pumped back through the cold plate. So here we have a few things going on. We have multiple domains. So we have air, water, we have fans, we have printed circuit board. We have a printed circuit board in there, which I will show you how to bring in using our EDA import. And then the goal of this analysis is to, assess the cooling capabilities of the fan, measure the pressure drop in the coolant, and then After the analysis is done, we'll add another step. We will conduct a trade-off study to vary the positioning of the fan and the geometry of the heatsink in order to see if we can maintain performance while reducing mass of these critical components. Now from here, I can jump into the demo portion of the webinar. Okay, so first thing, FlowEFD can also be launched through Teamcenter, so that's what I'm showing as the first step. So we have this assembly in Teamcenter. All of the project settings will be associated with this assembly. I'm launching the NX through managed mode, and then FlowEFD can be launched straight away from there. So once FlowEFD launches, you can see it is in the NX environment. We have the flow analysis ribbon and tab on the top and the ribbon on the side. We have all of our project settings. The only thing that needs to be done is the user needs to set a working directory so that FlowEFD knows where to store the output files. So your solution files, mesh, etc. will be stored in this working directory. So from here, I'll switch to the model itself. So as you can see, this is a native NX. And then I'm going to start hiding some of these parts to show what's inside it. So that's the top enclosure. That's the cold plate through which the coolant is running. So let me show you some of the other parts. That's the lower enclosure. Inside the lower enclosure, we have a fan. On the other side, we have the radiator, and that's the pump which is going to circulate the coolant through the coolant loop. And then I'm also going to jump into the heatsink and show you how the heatsink is constructed. So the heatsink itself has 4 rows of fins. As you can see, parameterized the number of heatsink fins on each of those rows. So we have Z1, Z2, Z3, and Z4 as the number of fins, and this is what we'll be using further to kind of, do a design optimization or trade-off study. So that's, these are 4 of the parameters on the heatsink. We also have a parameter over here. As you can see, we have the number of openings also parameterized, so we can vary that as well. And the last thing that we'll parameterize is the placement of this of this fan using a NX constraint. What I'm showing you here is a cross-section through the geometry, and as you can see, the parts highlighted in red are intersecting. FlowEFD can easily handle intersecting geometry using material priorities. So that's just some of the FlowEFD can do. Now I just launched FlowEFD through NX. The first thing we are going to do with any FlowEFD model is run something known as check geometry. Check geometry will let the user identify any issues with the geometry and also give you the final fluid domain inside your geometry. Let's do that. So as you can see, when we run the check geometry, you will see all of the fluid volume that has been identified by FlowEFD. So here we have the top enclosure, bottom enclosure, and also the fluid loop. So this gives us kind of a check and it's okay. And from here we can now switch to setting up the model itself. So FlowEFD sets up models through a wizard-based functionality. So first thing we are going to select, the physics, heat conduction. We have gravity. We select fluids. So air is our default fluid, but we are also going to add water because we have water in the coolant loop, aluminum as default solid. We can also set up analysis using a already saved. So I'm going to show that really quickly. So as you can see, the physics have already been selected and they have been obtained from the template. So a template is a good way of storing your best practices in the analysis. So here I'm showing you how the coolant loop was set up. So if there is an isolated fluid volume inside your assembly, you just have to select one internal face and then FlowEFD will identify that coolant loop. So that has been set to water, everything else has been set to air. Now I'm going to quickly show you some of the other things I have set up. For example, the fans have been set up using a fan curve. FlowEFD can, you can directly paste fan curves in FlowEFD, so volume flow rate versus pressure drop data, and then we have that internal fan which can use the incoming temperature as also the outgoing temperature, so you can create a fluid loop or a coolant loop. So this is the basic setup. We still don't have the PCB geometry in there. That I will import in the next step of the demo. So the EDA import is done using something known as the FLOEDA bridge. The FLOEDA bridge can import PCB data. It can import things like layers. It can import the components. It can also filter components based on the size, reference designator, power density, etc. So let me quickly import file to show you how that is done. So we can import file formats such as ODB++, CCE, IDF. Let me start the import process. We also have a few levels of modeling: compact, detailed, and material map. So each level of modeling can capture different kinds of things. So for example, compact is just all of the layers merged into one. Detailed, we can separate the layers and average the conductivity over there. And then the last one is material map, which is a for based on the copper and dielectric distribution in the printed circuit board. So as you can see, these are all of the supported formats. This is an open source board that I'm importing, known as the BeagleBone. So and of course the import process is being shown live. This just shows how quickly FLOEFD's EDA bridge can process this sort of complex EDA data. So once the board is imported, we'll go and see how the board is constructed. So let's look at some of the layers of the printed circuit board. So these are all of the components on the board without any filtering. Now I have turned on filtering to kind of remove some of the components which are not of importance. Now I'm going through the layers, and you can see, FLOEFD can capture all of that detail. And then we'll quickly set the modeling level to material map. And then the next step of the process is to show how to import a thermal list. So something like this is known as a thermal list, which has the reference designator, the type of modeling, the power dissipation, any junction to case, junction to board resistance values you may have. So you can quickly import your, the power dissipation on all of your components using a list like this, so you don't have to manually set up each and every component. The EDA bridge serves as a preprocessor for EDA data going into FLOEFD. So it will not only create geometry, but it will also create the necessary material properties and power dissipation values needed for the printed circuit board. So component U5 has been set up as a 2-resistor component, and the 2-resistor values have been obtained from the thermal list. So that's the only part we are going to model a little more detail. All of the other components have been just set up as a block with volumetric heat source assignment. So now that we've verified that our model looks okay, we are ready to transfer this model back to FLOEFD, and let's begin that transfer process now. Now, once the model is in FLOEFD, let's quickly review what the smart PCB or the material map brings in. So examining all of the layers, we have some filtered heat sources also, which can be added as a smeared heat source on the top and bottom. Component U5 is set up as a 2-resistor component, so that is also available in the tree. And we've also generated a goal for the temperature of that component. So the next step is to look at meshing. And what I'm showing you right now is just the automatic meshing. And the automatic meshing is typically okay for cases like this. This is the base mesh. All of the refinements are done on top of the base mesh. We are also going to set some bounds for the refinement of channels, and also going to close small regions below 0.5 millimeters. As you can see, I've set it up in closed-in slots. We also have some manual control you can see over here, which give the user a little more flexibility. But for most of the cases, this sort of automatic mesh setup is okay. So now let's quickly review the mesh and what sort of mesh FLOEFD generates. So as you can see, the mesh is Cartesian in the fluid region, Cartesian in the core solid region, but at the solid fluid boundary, the mesh is not Cartesian, the mesh is actually polyhedral. So that is known as a smart cell, where with one sort of overlaying Cartesian grid cell, inside that you can have multiple fluid regions and multiple solid regions. So as you can see over here, this is a fluid region, this is a solid region, and this again is a fluid region. All of that is sort of inside this Cartesian grid cell. This is known as a smart cell. So now that we've reviewed the mesh, we can also go ahead and look at some of the results that FLOEFD is able to provide. Again, that is just the mesh of the heatsink. So now let's review some of the goals. Goals are ways of monitoring the FLOEFD solution. So you can set up goals for points, surfaces, volumes, and so on. So here we have the inlet water pressure, the outlet coolant temperature, and we also have some goals for the mass of the lower enclosure and the heatsink, because that is what we are going to sort of optimize in the design study that I'm going to go over later. We have some calculation control options, as you can see here. This is a steady state run, so you can do based off of goals or the number of travels in the model, and you can select all of these goals as convergence criterion for the steady state analysis. Now you can run FLOEFD on your local machine, your laptop, your desktop, your workstation, or you can also run it on a remote machine. So you can also offload the analysis. So we have multiple ways we can solve for the solution. I already have a completed solution in this project, which I'm going to load, and now I'm just going to load the temperature distribution in the lower coolant loop. So let me resize that to the plot maximum and the plot minimum. We also have the ability to generate probe points. Probe points are just another way of interrogating the solution a little more. Sometimes the legend can be a little confusing. It doesn't give you enough, detail as to what the exact temperature is. For those situations, you can use probe points. And then we also are looking at the surface plot of the printed circuit board. So as you can see, I'm going to generate some callouts over here for the temperatures. And then let's also look at some of the fluid flow trajectories in the model. So in addition to the fluid flow trajectory, I've just turned on the PCB temperature. So as you can see, coolant flows through the top enclosure, and then air flows in the bottom enclosure. So all of that was visual. We also have the ability to extract all of the goals which are in the model and export them into an Excel spreadsheet. So not just numerical, not just visual representation of the data, we can also extract numerical data and send it directly to Excel. And as you can see, this is the history of the convergence of the temperature of the IC, which I showed earlier, the U5 component, which was modeled as a 2-resistor component. So as you can see, as the iterations are going forward, this kind of stabilizes and flatlines. So this gives us an indication that yes, the solution is indeed converged. So once you verify that the solution is converged, we can export it to Excel. We can also create a report, which will be based on a template. So this is, pretty useful for people. When you export the report, you have all of your input data, output data, goals convergence data, etc. This step of the analysis process is now jumping into the parametric study, which is going to be done through an intelligent design optimization software or tool known as HEADS. This HEADS algorithm is embedded in FLOEFD. It is an intelligent design search algorithm which will march through your design and then study the previous designs and then generate new designs. It doesn't generate the design space at the beginning of the analysis. It will only generate 8 designs once it studies the first 8 designs and knows the design space, and then it will generate 8 more designs. So HEADS will learn from the previous designs and then use that to generate the new designs. So let's look at what we can do over here. We are going to select, as you can see, the multi-parameter HEADS optimization. It can have multiple inputs and multiple outputs. So what we are going to do is we are going to add the NX expressions that we had created earlier for the parts like heat sink, the positioning of the fan, and also the number of vents on the front enclosure, on the lower enclosure. So I've added all of those. As you can see over here, I'm going to add the fan positioning. Now, we have added all of our ranges, and as you can see, once we've added the ranges and updated the ranges, so the count of fins on the first, number of fins in the first row is ranging from 30 to 160, all the way through the count number 3, Last count, that row is a little bigger, so we have that set to, a minimum of 30 and a maximum of 200. Fan positioning varies from, one side of the enclosure to the other side, and so forth. We have also set up these output parameters. So what are the quantities of interest? We are interested in looking at the mass of the lower enclosure, mass of the heatsink, and the temperature of the component we spoke about earlier, the U5 component. And then, as you can see, I have run about 100 design scenarios here already. And then based on these 100 scenarios, HEADS will tell us how to interpret the design space. In addition to giving us the optimal design, we also will know where in the design space we have good designs. So it will tell you which designs are better, which designs fit your criteria. So there's an envelope of designs which will meet your criteria for mass and temperature, and that's what HEADS is going to show us. So the next step is now I'm going to switch to something known as a parallel plot to show you how to interpret that design data. So let's now review what we saw earlier, what HEADS was able to do. So as you can see on the left, we have our baseline case where, you can see the flow direction coming in from the top and flow leaving from the bottom. Z1, Z2, Z3, Z4 are the heatsink fins. And then on the right, you can see the optimized design. The optimized design, as you can see, is not even, it has a varied distribution of fins on each of these rows. What HEADS was able to do for this specific design was it was able to reduce the mass of the heatsink by 14% while keeping the junction temperature of the IC similar to the baseline case. So the baseline case was 14% heavier. It still resulted in the same junction temperature as the optimized case. So those are the kinds of trade-off studies we can do with HEADS. And in addition to that, this is the design space. So HEADS will tell you how to interpret the design space. So this plot is known as a parallel plot. It has the outputs all the way on the left. So the goal is to minimize the temperature, mass of the lower enclosure, and mass of the heatsink. And as you can see, I have arrows that show that, say the objective is to minimize. What we see on the right of those are the counts, so counts Z1 through Z4, and then fan position and width of the opening. So what HEADS is telling us over here is, a low mass, low temperature design modify the heatsink by increasing Z1 and Z3 and eliminating Z2. Apparently, the row Z2 is not doing much, and also reduce Z4. One sign that HEADS is pushing the design limits is if you look at Z2, the best design is hitting the minimum. So for Z2, it's hitting that lower bound of 30. So that means that HEADS is trying to, sort of go to that lower bound. So there is, opportunity to reduce that count further. And of course, some of the other things are fairly straightforward. The width of the openings needs to be maximized for maximum airflow, and also the fan position is kind of biased towards one side, so biased towards the minimum. So this is what the design shows. The area you see in blue is better than the baseline design. So that is your envelope for, meeting your design requirements. The lowest mass designs are shown in green, and the best design is shown in yellow. The baseline design is shown in gray. So in the next slide, so here I'm just showing you all of the designs HEADS ran through. So 100 designs were looked at in about 100 hours. The best design improved the heatsink mass by 14%. These sorts of components are usually, mass produced, so they could be hundreds of thousands of millions. And if you're saving 14% on one component, that could actually, result in a significant, cost savings when you're, producing at that level. So yeah, the next thing I'm going to show you here is something known as the package creator. The package creator is a way to model IC packages, MOSFETs, etc., in a higher level of detail than just a 2-resistor or simple block-like representation. So what the package creator does is it lets you create packages using a template-based approach. You can also create a library. As you can see here, I have a library of a few components over here. These 3 components in my library. Now I'm going to switch to templates and show you the options we have. So currently inbuilt, we have all of these templates. I'm going to select a QFN style package. I'm going to define the QFN based on, some of the dimensions I found on the BeagleBone board. So we have, it's 4x4. The pitch is, we have 16 leads. We can also assign the thermal power to this. So the package creator, just like the EDA bridge, not only generates the geometry for these designs or packages, it also creates material properties and, boundary conditions. So it assigns the thermal power, and then you can assign the length of the die, width of the die, and what sort of package is it. You can have thin, ultra thin, or very thin. And then the next step, I create the package, and let me quickly hide the encapsulant to show you the details which are captured in the package creator. So once I hide the encapsulant, you'll see things like the die attach, bond wires, and the leads. So these are the, all of the details that FlowEFD can capture, or the package creator can capture. Now there are some things which can vary in addition to the things that have already been set. So as you can see here, you can vary the diameter of the bond wires. You can select detail versus compact modeling. So as you can see over here, compact modeling, what it does is instead of modeling each lead individually, it kind of creates, it creates a sort of a bigger geometry, and that can, simplify and make the simulation faster. And then we can also assign the material property for the bond wire through the drop-down list or the database. You can, choose any custom property, and then things like the die attach, encapsulant, lead frame, those can also be changed. So we, from here you export it out as an XML file, which FlowEFD can import. That's what I'm going to show you next. So let me show you where this geometry sits. So hiding the enclosure, hiding the cold plates, and then I'm going to zoom into the model and show you where this geometry lies. So it lies over here. So that is the component we are going to replace using a component from the package creator. This is also touching on another, very useful functionality in FlowEFD. We can access these components through a library, and we can build model in a way that, CAD designers assemble CAD geometry. So this BeagleBone project is going to set up using the package creator. Then I'm going to add this project to the top level assembly, and then FlowEFD will pull all of the conditions, material properties, etc. from that project. So this setup only has to be done, and then you can add it to any other project if this PCB is being reused. So now I'm going to import that file that I created earlier through the package creator, this XML file. Once the import is complete, you will see that this component is placed in 000. It, of course, needs to be moved to the right position. So I'm going to use assembly constraints and NX move commands or move component commands in order to position this component to overlay the simple geometry. And once that is done, I will sort of deactivate that simple geometry using component control in FlowEFD. So now that both components are overlaid, we can, set up our analysis. I'm going to quickly show you what it looks like once it's in position. I'm loading some of the results. I'm showing here the temperature distribution on the printed circuit board. So as you can see, if you notice the simple components, there's not a lot of temperature variation on a lot of the simple components, but I'm going to zoom in to show you what the temperature distribution looks like. What I've done here is I've hidden the encapsulant to look at the temperatures in detail on things like the die attach, and the bond wires. So I'm showing the mesh and also the temperature plots over here. So these kind of like detailed temperature distribution plots will probably not be achieved by using simple components, and that's kind of what I'm trying to show you here. We've captured all of the bond wires and the small leads, etc. So this is the sort of detail to which you can model a package for EFD.
Picking up from where Adil left off, let's go ahead and look at sort of the electronic-specific capability of FlowEFD. Some of you may be aware of FlowEFD, know that it's this CAD-embedded tool, but don't necessarily know, a lot of the depth that FlowEFD has with respect to electronics cooling. And in truth, a good portion of it is is newer within the last couple years. So that, that could contribute to that. But let's go ahead and just understand a lot of what is available, starting, sort of on the smaller scale, and we'll move up from here. So at the component level, obviously there's different ways to model ICs. Adil just took us through a few of them. So from compact to resistor to a network assembly approach like a Delphi representation. We have compact models like thermoelectric coolers, heat pipes, thermal joints. There is a nice way of modeling LEDs, which I'll touch on here momentarily. Connections to some of our hardware for sort of higher fidelity models that you can use FLOEFD to simulate. So talking about the ICs, we have basically from the simplified approach to resistor, which is probably the most common method out there of modeling ICs when trying to get a junction temperature, but oftentimes that's not enough. So moving to something like a network assembly, or then ultimately an explicit representation like Adil just covered with the package creator. So the very nice tool utility that lets you kind of step your way through defining a package, and then you have the reusability of that package in in other FLOEFD models once you've defined it in package creator. It can address the different levels that you want to model your chips with. As you move to the board level, certainly things like the EDA bridge, which Adil showed in his example, really powerful tool, lets you take EDA data and in the most efficient way have a representation of that board in your thermal model, depending on the level of detail you need, whether you're down at the board level versus in a system level. You make these choices in the EDA bridge, filtering out devices, making choices about how you want the board itself to be modeled, having sort of the optimal type of representation of that board for your analysis needs. That includes being able to do things like joule heating, and that impacts, like I say, some of those choices you make. You may decide to include various traces explicitly, but then for the rest of the board, model it in a different way. Probably the most interesting one and powerful one is the one that Adil showed in the demo, which is that newer material map option, that smart PCB that it essentially creates a massive thermal network using more of a 1D network style approach to model all the copper distribution in the board. And you get this great balance between a lot of accuracy through the detail without the overhead of classic 3D ways of trying to represent all that geometry. So different options with respect to your board modeling. If you are doing joule heating, there are electrical elements which let you, let's say you have a circuit with components in the circuit that are fairly detailed that you don't want to include. You can swap those out with these electrical elements that let you give the appropriate electrical resistance without needing to have that detailed model and still be able to close the circuit. So that's another nice option with respect to joule heating. If the package on the board is one that you actually have data available, we have, of course, hardware that does things like thermal characterizations of ICs, like with our Tristor hardware. So if you're using that, you can make use of that data to do what we call calibrate your package in your thermal model to give you a higher fidelity model. And along those lines, again, tying into our hardware, if it's an LED you want to include in your analysis, you can use additional data from our hardware, including the light output data from a TeraLED device along with the Tristor data to give you this compact model of an LED, really convenient and powerful, where the input that you're giving it is just a forward current. You're not giving it a heat generation rate, for instance. You give it a forward current, and then from the analysis, you'll get the resulting junction temperature as well as the luminous flux that LED is putting out. As you move to the system level, of course, various types of problems, conjugate heat transfer problems, including bringing, radiation into play, and we have, a range of higher-end radiation capabilities with the software. You can, of course, have fans, like there is a battery modeling option with FLOEFD. You can start to include some physics, like humidity or surface condensation if that was relevant to your problem. So a range of capabilities as you move up to that larger scale at the system level. And one of the more interesting recent advances is the reduced order modeling capability. So for a certain class of problems, if it meets the assumptions of this approach, you can make use of this technology. And basically, it gets down to having a linear problem, linear conduction problem. Let's say you have something that has a very transient set of inputs, like rapidly changing power inputs, throughout the device. So it's conduction dominated. You can include the convection effects through heat transfer coefficients, but you're not going to model the fluid space. But you can take that type of model and through this ROM extraction process, be able to solve what would otherwise be in a 3D CFD environment, a very long-running analysis, and massively shorten the time it takes to solve that type of problem. So, this isn't going to apply to every type of thermal problem you're going to run into, but for the ones it does, this can be a very powerful way of getting that information. And then as you move to other types of effects that are relevant to your thermal problem and need to bring in maybe EM effects, we can co-simulate with Simcenter Magnet to bring that aspect into the analysis. So maybe just finishing with I picked one customer testimonial slide from a host of our customers to show this is a case where working on a detailed CAD assembly was very attractive, very appealing, and that's how this company uses our software to be able to do these complex thermal analyses directly on their CAD models. So if I gave just a couple concluding remarks about this, the big thing that we're trying to convey here is this notion that if it suits your workflow, if the idea of doing thermal analysis of electronics in CAD is appealing, then there is a tool that's very powerful that can do that, and that's FLOEFD. This isn't necessarily the only workflow, and there are certainly reasons that, based on either the engineer, the user that's going to be using the software, or potentially the application where the workflow is more appealing to be in a dedicated electronics cooling tool. Certainly as Siemens, we have that available as well, and that is historically how thermal analysis has been done. So part of what this is about is making aware that there is another option if that is suited to your desired workflow and the application you're trying to analyze, is being able to leverage some of the advantages of working directly on the CAD model in that CAD environment. So that is available. Some people may have known that there is CAD embedded options to do CFD, but they just thought it likely lacked the depth of the electronics cooling capability. And with FLOEFD, that you have that available to you as well. So that is front-loading electronics cooling with CAD embedded CFD. I will go ahead and pass this back to Jay, and we'll finish up.